Welcome to our presentation. Erica and I decided to do our final project on students attempting to pass examples on as proofs.
We did research on various definitions of proofs, and they all contain the fact that proofs are mathematical arguments, and they all follow one logical step after another. We made our definitions based on our research.
So now that we have defined what a proof is, let's talk about different types of proofs and what they are intended for. A very common type of statement that requires a proof in mathematics is an if-then statement. These types of statements contain a hypothesis P and a conclusion Q, such that the statement is in the form if P, then Q. So first, let's talk about a direct proof. These types of proofs first suppose that the hypothesis P is true. Then, through the use of definitions, axioms, and computations, we then conclude that the conclusion Q must also be true. For a proof by contradiction, we first suppose that the hypothesis P is true and the conclusion Q is false. Then, through definitions, axioms, and computations, we derive some sort of a mathematical contradiction. For example, 0 equals 1. Because of this mathematical contradiction, we're then forced to conclude that the conclusion Q must be true. For a proof by contrapositive, we first start out with supposing that the conclusion Q is false. Then, through the use of definitions, axioms, and computations, we then conclude that the hypothesis P must also be false.
In multiple studies, it was observed that students pass examples as proofs. These middle school and high school students were able to identify rules and patterns, but they were not able to explain why it occurs. One main reason this misconception exists is because students in K to 12 grades generally do not get the opportunity to work with proofs outside of the geometry class. Even though proofs are necessary for all domains in mathematics, proofs themselves are not on the Common Core curriculum beyond geometry. Teachers do not teach conceptually. Since many teachers themselves have not received conceptual instruction, they may not know how to provide this to their students. Students have a misunderstanding of proofs as a reflection of their instructional experiences. Since students have been exposed to only procedural instruction, they believe that mathematics is about routine and procedures. Teachers not working on proofs with students is a disservice, especially to those who want to go on to undergraduate mathematics. Students often graduate high school without the experience of writing proofs outside of geometry. Cohen Ruthven discussed a study that was asked students to prove various obtainable mathematical prompts. Students had to define what a proof is. Students defined it as something that is useful, a general formula, or a super check. When they were asked what was the purpose of the proof, students generally answered, it makes them feel more confident and assures them that one is definitely always correct. Oten et al. Discussed another study where students' understanding of proofs at a pre-algebra and algebra level were analyzed. And this was analyzed through a discourse. Their research suggested that many students provided examples from some distant authority because they view mathematics as a collection of procedure and rules. In the study by Nad et al., there was 350 middle school students, and they were asked to prove 15 mathematical statements in 45 minutes. It was their typical class period. The assessment items require students to evaluate various arguments, generate their arguments to demonstrate understanding of implication, rules, and deductions, apply definitions, and discuss the nature and meaning of proofs. One of the prompts asked students to prove that the sum of two even integers is an even integer. In order to write a formal proof, students needed to know the definition of the sum and even integers. These students proved this mathematical statement by providing examples that were enough, it was enough to convince themselves and their peers.
Okay, so the results of the Newth et al. Study showed that students consider 5 strategically planned examples as sufficient to convince their peers that a mathematical claim is true for all cases. In the prompt where students were asked to prove that the sum of two even integers was an even integer, they gave examples such as 12 plus 8 equals 20. But this is just an example. This is not proving the general case. In a study by Stavru, who studied undergraduate mathematics students in their first proof-based course, he gave them the prompt of an if-then statement. If A divides B and B divides C, then A divides C. The students attempted to pass this on as a proof. Suppose A equals 2, B equals -6, and C equals 12. We know that 2 divides -6, -6 divides 12, and 2 also divides 12. But notice that this is just an example. It doesn't prove the general case. Note that this is also a strategically planned example with a combination of negative and positive integers, but it does not constitute as a proof. Okay, so here is a correct proof. This is a direct proof supposing that the hypothesis A divides B and B divides C is true, and then concluding that the conclusion A divides C must therefore also be true. So we use definitions of what it means for an integer to divide another integer. We have ax equals b and by equals c for some integers x and y. And then by computation and substituting ax in for b, we have axy equals c. Then we have a little note that xy is an integer, and therefore the conclusion a divides c is true. Notice that there are no numbers in this proof, written anywhere in this proof. This proves the general case.
All right, so in our personal experience with proofs and proving. So while working together, Maya and I noticed that we had a lot of similarities when it came to our experience with proofs and proving, especially in our secondary mathematic level courses and then going into college. In our secondary mathematics experience, Maya and I covered proofs during only geometry, and unfortunately, it was only a short unit. We received instructions through examples. Therefore, we walked away believing that examples were good enough to support our claim. So when we attended college as undergrads, we struggled so much with proofs. And unfortunately, we had to learn everything all over again. So learning proofs the correct way felt like going back to the very beginning, and that everything that we had learned was finally getting explained since we only knew of these examples. But unfortunately, even after graduation and trying to teach this concept to our students, we just didn't know how to do it. So we just taught our students the way that we were taught. Unfortunately, teaching our students this way, our students also walked away with the same misconceptions that we once had. After attending class, doing readings, and doing all the research, we started making changes in our classroom. We created a new classroom culture where proofs are more acceptable and students are, having discussions. They take part in the discourse, they have arguments with each other, they use collaboration boards to share their ideas and reasonings, they use proof outlines, and we have modified the problems to provide our students the opportunities so they can also get exposed to forward and backward methods to expand their proof abilities.
Thank you for attending our presentation.